Okay. All right. So welcome everyone to the 44th episode of the SFU Sports Analytics Virtual Seminar Series. Today we have Dr. David Radke, who's going to discuss with us presenting multi-agent challenges in team sports analytics. So Dr. Radke is a senior research scientist for the Chicago Blackhawks of the National Hockey League. Originally from California and a US and Canadian citizen, David attained a BA in computer science with a minor in discrete mathematics from Colorado College and a PhD in computer science from the University of Waterloo in 2023. His PhD thesis is entitled The Impact of Teams and Multi-Agent Systems. His academic accomplishments are supplemented with real-life experience as a varsity hockey player at both of the institutions. Colorado College plays in the NCAA Division I hockey, and also with Waterloo in U Sports. So that's pretty cool. And you can learn more about him at his excellent website shown at the link below. In terms of, there we go. In terms of the talk, so the talk today will present several challenges and opportunities within the area of team sport analytics and key research areas within multi-agent systems. Multi-agent systems is a subfield of distributed artificial intelligence. They can be defined as a network of individual agents that share knowledge and communicate with each other to solve a problem that is beyond the scope of a single agent. We specifically consider invasion games where players invade the opposing team's territory and can interact anywhere on the playing surface. And so the salient examples are ice hockey and soccer. And he will discuss how multi-agent systems are well equipped to study invasion games and will benefit both the field and sports analytics field as well. And it'll highlight topics along two axes: short-term strategy or coaching and long-term team planning at the management level. A paper based on this work is posted to archive, as you can see there, and then I've shown the reference below. And with that, I will stop sharing my screen and hand it over to you, Dr. Radke. Welcome.
Cool. Thank you. Thanks, Dave, for that great introduction. Let me share my screen, get my presentation going. Okay. Can you guys see the presentation okay?
Looks great to me, David.
Okay, cool. Thanks. Yeah, thanks, Dave, for the introduction. Thank you, Oliver, for the invitation to come to SFU and give this talk. As mentioned in the introduction, the title of this talk is Presenting Multi-Agent Challenges in Team Sports Analytics. My area of research is within multi-agent systems. The first part of this talk will actually be most relevant to this title. I decided to augment kind of the second half of the talk with some more applied work using actual hockey data that I've done both during my PhD and then since my PhD. So as mentioned, my name is David Radke. I'm a senior research scientist with the Chicago Blackhawks. And I'm really just gonna begin by highlighting kind of the interesting relationship that AI has with games and a bunch of different types of games. So here I have a bunch of examples of how researchers have used, say, board games to help develop new artificial intelligence algorithms. And so there's several motivations behind this, that these are zero-sum games. They're easy to benchmark and use as yardsticks for progress. And so we've gotten to the point in a lot of these board games where AI has actually learned to beat the best human players in the world. And so this isn't just limited to board games. We've also seen kind of the development of AI algorithms in kind of more complicated board games, such as diplomacy, card games like poker and Hanabi that sometimes have incomplete or imperfect information and then also require cooperation, which is cooperation is very difficult for reinforcement learning or typical AI models to learn. And in the scope of reinforcement learning, these aren't just limited to, say, real-world games or board games that that can be simplified into video games. But the development of AI has really been coupled, especially reinforcement learning, with kind of simulated environments, online games, and these are sometimes sporting related, such as the RoboCup series. That's been going on for over a decade now, 2 decades maybe. And that's in the virtual world, in the real world here down on in the bottom with the robot. And then also a cool one, Sony AI developed GT Sophie, or Gran Turismo Sophie, which I was actually an intern on that team for a bit, and developed an agent, a reinforcement learning agent, to learn from scratch to beat the best Gran Turismo racers in the world. And so what's interesting is that with this development of AI and all of these kind of simulated environments and kind of testbed environments, we've also seen AI applied to real world sports in a bunch of different interesting contexts. So there's obviously lots of computer vision problems in real world sports, such as player tracking, limb tracking, pose estimation. Oliver and has some interesting work on kind of learning player embeddings from hockey data, hockey event data. There's also been a lot of work in AI that actually uses sporting data for evaluation. So down here, this is a team formation paper, which is really interesting about learning the value of different players or different groups. And then also, I think kind of the connection between AI and real world sports is really kind of emphasized by the collaboration between DeepMind and Liverpool FC, and down here in the bottom left, and they recently just published a Nature paper. The original version of the paper came out in October, but called Tactic AI, which tries to learn the value or probability of different actions and the value of different actual structural formations on the pitch and corner kicks. So it's very interesting work, and I encourage you to go read the paper. And so progress at the intersection of AI and sports analytics ultimately relies on the characteristics of the game and of the sport. And so here, I just want to give an overview of artificial intelligence as a field. This is by no means encompassing of the entire field, obviously, but these are just like general areas. There's obviously natural language processing, computer vision, and then we have AI in the middle. And in this talk, I'm really going to lean on multi-agent systems. And so multi-agent systems is my traditional area of research, and it's kind of one of the smaller areas of AI, I'd say, but it is massively important when you think about how we interact with AI. The multi-agent systems are defined as environments where there's multiple intelligent interacting agents. So you can think of this as a population of people or virtual agents or robots, kind of maybe the mixture of robots or virtual agents and humans. And so within multi-agent systems, I'm also going to talk about reinforcement learning and deep learning. And these are all kind of coupled together because we might have intelligent agents that learn through reinforcement learning, which is supported through deep learning within the domain of deep RL. So this talk is split up into 3 different parts. And there will be kind of these natural breaks after each of these parts that kind of we can ask short questions if anyone has any. But first, I'm going to go into multi-agent challenges. This is drawn mostly from a Blue Sky paper in AMOS last year. And so what that means is it's kind of a position paper, and these are trying to present new ideas to the field. And so AMOS is the main multi-agent systems conference, and it's really trying to make this connection between a certain class of sports and multi-agent systems. And so I'm really going to highlight 2 different classes of sports here. There's multiple different classifications, but these 2 will help me get my point across. So in the early 80s, Ellis identified different types of games. The first I'm going to talk about are striking games. So striking games are those where players strike objects into open spaces, and the other team places fielders strategically to prevent runs. And so you can think of this class as containing sports like baseball and cricket. And so obviously analytics and baseball has played a huge part in the development of the game in the last several decades. This initially started with Moneyball and sabermetrics, and the idea here is using empirical statistics as a basis for roster management. So I'm emphasizing the word statistics as things like on-base percentage, slugging percentage, batting average, and I'm really want to emphasize the word statistics and come back to that in a few slides. The second class of games that I'm going to talk about are those termed invasion games. And so this is the class of games where teams intermingle and attempt to outscore the opponent by invading the opponent's territory. And so you might think of these as ice hockey, football, or soccer, and basketball. And so the point I want to make here is that when we think about trying to model invasion games analytically, these games are inherently a lot more complex because there's a lot more interaction between players. There's a lot more coordination and teamwork needed for success. The data is a lot more complex. There's a lot more strategic freedom when you think about different strategy spaces. And so in invasion games, it's not just about who is good, but identifying who's good together and in what scenarios. And so the main point of the Blue Sky paper and the main point of the first part of this talk that I'm going to kind of try and highlight is that multi-agent systems is to invasion games what statistics has traditionally been to striking games. And that progress at the intersection of multi-agent systems and invasion games will really help drive both fields forward, analytics and invasion games and multi-agent systems. Research at the intersection there will really help drive both fields forward. And some kind of motivations for why I believe that is that why I think multi-agent systems and invasion games are kind of well suited for each other, or that invasion games happen in enclosed environments, much like the simulated environments that we have in the first few slides. There's real examples of cooperation and coordination in invasion games, both good and bad. And as I mentioned earlier, agent learning cooperation is really challenging. There's different structures to the teams in invasion games. So you might have different positions: forwards, defensemen, center backs, attack. And then if you think about hockey, like within those positions, there's also lines and pairings. Success and trying to navigate these games happens at multiple time scales, coaching and management, which I'll talk about more. All of the problems here are augmented by marketplaces. There's contracts that players need to sign. And then what's nice about this is we can collect data on a lot of these things. So the two data sources I'm going to talk about are event data and tracking data. And these will also help support the second and third parts of this talk. So the first I'm going to talk about is event data. Just a quick overview. Event data are things like shots, passes, carries, possession gains. And so event data gives you the XY coordinate on the playing surface and the player that shot the puck or passed the puck. There's about 3,500 events per NHL game, but we don't really get the general context of the game. We don't get the positioning of all the other players, and so the state space is kind of augmented away. The second data source that in hockey we get at the NHL level, and soccer and other sports, there's tracking data at a lot of other levels. And so tracking data gives you the X, Y, and Z locations of all the players on the ice or the pitch multiple times per second. And essentially what you can do is, in theory, is you have tracking data and event data, and you can perform a join so that when there's a pass or a shot or a possession gain, you kind of get a richer understanding of the state space as to the context of when this action was taken. This is kind of what the larger state looked like. And so in the NHL, this tracking data is collected via a hardware system as shown on the right. However, in other sports, this is sometimes a computer vision problem. And so to highlight kind of the interaction between multi-agent systems and invasion games, I'm really going to talk along two different dimensions here. So the first is coaching and the second is management, more longer term problems. And one thing I really want to emphasize here is that these problems don't really, or these axes don't really operate in isolation. They inform each other. And so whatever coaches do in the short term, in match or prior to a match, ultimately impacts the team's standing performance and the draft position that management has at their disposal to try and build a team. And then whatever players and coaches or management ultimately impacts whatever coaches and players have to work with. So the first I'm going to talk about is coaching, and these are short-term problems. These are before or within match. And so the way I'm going to go about highlighting these axes is I'm going to kind of emphasize these big overall or overarching questions. And then I'm going to pause for a few seconds and let you think on your own experience about maybe things within your own areas of research or areas of expertise that you would use to try and solve these problems. And then I'm going to circle back and I'm going to kind of highlight overarching areas of research within multi-agent systems that have tons of overlap with all of these questions. I have hidden slides at the end about some of the challenges in adapting multi-agent systems solutions to these problems, but I won't get to those unless we have extra time. So the first for coaching is coaches need to identify which players play well together. They also, in doing this, need to identify how much do players and groups contribute, so measuring that accurately. And then coaches also need to devise and update strategies to beat their opponents. And so I'm going to pause here for a few seconds, just think to yourself about, in your own experience, how you would kind of go about approaching these problems. So some general areas of multi-agent systems that are relevant to the first one are kind of the areas of team formation or coalition structure generation, figuring out which players can work together. This obviously deals with offline policy evaluation, understanding how much do players and groups contribute. There's the area of agent types, or more commonly known in sports as archetype, the archetype of a player, which archetypes might work well together. This might be continuous, so you might have some degree of different archetypes. Agent types in reinforcement learning and in multi-agent systems is a big area. Understanding how much players contribute is ultimately a problem of value decomposition. So a line goes out, they get a goal. How much does each player contribute to that goal? Value decomposition is a huge area in reinforcement learning and multi-agent reinforcement learning. And then kind of devising and updating strategies to beat opponents brings in this whole other area of multi-agent systems, which deals with game theory. So trying to come up with kind of like trying to condition on what you would expect your opponent to do. So this might require opponent modeling, multi-objective optimization. So coaches might not just want to construct lines that would maximize, say, goals or expected goals. You might kind of want to optimize for multiple objectives like goals or minimizing goals against or expected goals against. So these are just general areas of research within multi-agent systems that have significant overlap. The next axis I'm going to highlight is management. And so management, these are longer term problems. These are across multiple matches or multiple seasons even. And so I'm going to go through the same format. Some common problems that management deals with is they first need to analyze their roster and identify areas for improvement. Once they've done this, they then need to have the problem of actually constructing a team through drafting, signing, and trading. So getting that collection of players for coaches to work with. And then what's really interesting in professional sports is that this all needs to be done within economic constraints. So in the NHL, we have a hard salary cap. Other leagues have a luxury tax, or say the budget of your team. And so this is kind of a constrained optimization problem. So some areas of multi-agent systems that are significantly relevant with these problems are to analyze a roster and identify areas for improvement. This one area here is to understand role diversity and distributions across your team. Obviously, the team formation problem deals with different roles. This might incorporate offline RL or imitation learning to try and learn what the policies of the agents or players you have on your team. Policy evaluation, trying to evaluate how good a different or a specific policy is in a specific role. To actually construct a team through, say, drafting, signing, and trading, this ultimately is related to the problems of in ad hoc teamwork, where in multi-agent systems, these are designing agents that can learn to coordinate or work together in a zero-shot setting. So trying to understand which types of players might coordinate together best. Policy prediction is a big one, say for drafting. In the NHL, we draft players when they're 18, and they might not show up in the NHL until they're 21, 22. So predicting what their policy might look like in different contexts, that's also a big one in multi-agent systems. And then operating within economic constraints ultimately deals with things like game theory, because there's a lot of negotiations, bargaining in terms of different types of games in an unrestricted free agent setting. The game in that case is dealing with 32 or 31 other teams and the player you're trying to negotiate with. The actual negotiation is a two-player game. So there's a lot of these kind of sub games within game theory that kind of tie into these notions of bargaining and negotiations. And then obviously constructing a team deals with problems of resource allocation and fair division. This is a huge area of multi-agent systems where, say, there's divisible goods or indivisible goods, and you kind of want to allocate them across a population. There's different axioms of fairness depending on what agents probably deserve what, given some notion of performance. You might be familiar with the Shapley value. This is kind of stems from that area of research. There's a lot of overlap with that in economics in that space. So with that, I'll wrap up the first part of this talk talking about multi-agent challenges. Are there any kind of shorter questions about the first part here?
Yes, Dave, I'd like to ask a question. I'm actually really just interested in what you have to say, because I've asked this question before. The question is, what is the definition of AI? And more specifically, when does an algorithm become AI?
Okay, thank you. Thanks for the question, Tim. I mean, I feel like there could be a fairly like philosophical question or answer to that question. In terms of when does an algorithm become AI, in my view, and I'm probably being overly simplistic, or maybe just like encompassing too much, but I guess when an algorithm has the ability to take an action or make a decision, because that kind of like takes expert systems into account, as well as like classification or regression algorithms. Like they make the decision of what a value should be. I'm sure there's a lot that I'm not accounting for there, but I hope that kind of answered it. I'd probably have to sit down and think through that for a little bit longer to give a better answer. And that's also me coming from like a multi-agent systems reinforcement learning background of like taking actions in specific states, given the context of your whatever state you're in. So anything else?
Yeah, maybe a question, but it could be a comment for later. You mentioned Shapley value, so I'd be interested in your thoughts on whether that's a helpful concept for evaluating player contributions and maybe even evaluating, pairs, groups of players. I mean, maybe that's something you get to later in the discussion, but just wanted to flag that. I think that's interesting.
Yeah, I mean, just a quick note on that. Like, it could be there. The Shapley value is also somewhat restrictive in terms of like assigning value. Like, the axioms are pretty hard there. There's actually someone in my lab, a master's student in my lab at Waterloo, who went to UBC for his PhD. I believe he's still there. His name's Greg Dion. And he had a really nice paper where he had a bunch of simulated games and then kind of did a user study and saw whether people follow the Shapley value and how they allocate rewards or allocate payoffs to the agents involved. And he actually found that humans violate the axioms that the Shapley value is designed to uphold. And so in that paper, he kind of suggests kind of data-driven axioms that are more aligned with how humans would allocate value. It's very interesting. But yeah, I'd obviously like there's a bunch of different ways to assign value. They all probably rely on context, but Shapley value is one way to do that. So
Thanks.
Cool. So yeah, I'm going to move on here and talk about learning value functions from data. And so I mentioned two different data sources previously. This one is going to deal with event data only. And so Oliver has some similar work, which if you've seen any of Oliver's talks, the model, it's not quite the same, but it kind of has similar aspects. And so here we want to learn a value function. This is heavily in line with reinforcement learning, where you're in a state and there's some value of being in that state. And there's also some state action value function. So there's some expected value of taking an action in a specific state. And so the goal here is to learn the value of a game state from offline event data. So the challenge here is that event data comes from two adversarial agents, and it's all in one stream. So here I just have like one little sample of event data, and you can imagine like this is augmented with a row or with a column about team information. So here we have team A takes different event actions than team B. And then somewhere down the line, there's a goal or a shot or some event that we want to treat as a termination state. And so the structure of how these events come in isn't really well defined. Like team A could take 3 events in a row, team B could take 2, could take 5, could take 10. And so there's some challenges with dealing with the event data in this way. If we want to just learn a value function from this data, from one data stream with 2 adversarial agents, it's not simultaneous move, as I explained. In the real world, a game like hockey is simultaneous move. Players all act at the same time, but the way that we actually record data and the way that event data comes in is not simultaneous move. It's also non-Stackelberg. As I mentioned, it's not like a turn-taking game. It's kind of like one agent, which would be a team in this case, takes a bunch of actions, and then another team could take a bunch of actions. And then it's also very sparse reward. There's only rewards, say, if there's a goal or a shot or any event you want to treat as a termination state, which are typically very sparse in hockey. Now, with the challenges, there's also several advantages that we can leverage to try and build a model around this. We know, for instance, that, say, if we have 2 teams, 2 agents in this game, 2 players in the game theory sense, we know that there's zero sum. We know that the 2 teams are adversarial, and we know that there's exactly 2 teams and 2 agents in this game. We know that there's a defined reward structure, in that if we want to define the reward to be a goal or a shot, we know that there's an explicit structure behind those events. And then we could also say learn a reward model, which could be an expected goals model. So in reinforcement learning, there's this notion of learning a reward model. more typical in like offline reinforcement learning. But here we could learn a reward model for this offline reinforcement learning problem. And that reward model could be an expected goals model, more typically known in the sports analytics world as an expected goals model. And so the way we're going to approach this problem is essentially learn a value network that uses kind of the Bellman update typically used in reinforcement learning. So here we have the Q value, and then like we have kind of the Bellman update where we have some learning rate, we have a discount factor, a reward, other Q values at time t, for the next state, next action, whatever. And we're going to augment this Bellman update with a parameter beta. And so what beta is going to do is essentially give some signal as to what team the event belongs to. And that signal depends on the downstream reward of some trajectory. And so when we perform this update, we can actually lean into the fact that the game is zero sum and we know that there's two agents. And so we can actually learn these reward functions dependent on whatever the downstream reward is. So some overview of the results. The next few slides are for the 22-23 NHL regular season. There's 4.2 million events included at all different man powers, all different score differentials. This was over 1,300 games. There's over 1,000 different players that made up the data set that generated the events, and obviously there's 32 teams. Now, I will say, like, here we assume that we are learning one value function for the league of the NHL. So you could obviously parse this to learn one for one team or one for one player. But the first kind of result I'm going to show is learning a policy network. And so a policy in reinforcement learning and in multi-agent systems is essentially how agents behave in different states. And you could think of this as a probability distribution over different actions that they can take. And so here, the state in these cases are each location on the ice, and then darker red here indicates a higher probability of taking this action in this state. And so each rank here represents a different action that the agents can take. And so again, as I mentioned, we do this for the whole league. So what we're learning in this policy network is essentially a league-wide policy for the NHL. We're not doing this for just the Chicago Blackhawks. We're doing this for the entire league. And so once we have the policy network, the next thing we want to do is learn a state action value network. And so what that means is we want to learn the value of taking an action in a specific state. And so we have the same setup with the rinks here for each different action. And then darker red values here represent higher expected value for taking that action in the specific state, the specific area on the ice. And like score differential and manpower, stuff like that, whatever you want the state to be. And then darker blue represents kind of less value or more negative value. And then white represents equality at 0. And so once we have the policy network and the state action value function, we can kind of combine these to create the state value function, or put simply, the value function in reinforcement learning. And so what this represents is the expected value of being in a state. It's not just taking an action in a state, it's the expected value of being in a state and then following whatever policy you have afterwards. So here you can see that darker red represents higher value. And so what we actually learn through the NHL data is this kind of shape of higher expected value around the offensive goal. And what's really interesting with this is because we have the policy network and we have the state action value network, we can kind of do what deep RL or deep Q learning agents do. And we can say, okay, assume you're just going to take the max action, or the action with the highest expected value in a specific state. And so here we can just say, like, okay, what's the highest value action in a specific state? And we color it based on whatever this action is. And what's interesting is that around the offensive goal, we see that shooting has higher expected value. But as you get kind of further into the corners, we see that in the offensive zone, we see that passing has higher expected value, because one might imagine that the value of passing the puck from the corner to an area of higher expected value, say in front of the net, causes passing from the corner to ultimately have higher expected value than shooting. Now, I'll say the caveat here is that this is all in expected value space. So it's not saying that a player in the corner, if they choose not to pass it, that's the wrong decision, because obviously it depends on the context of the game, kind of the higher dimensional state space of where all the players are and stuff like that. So this is as much of the results I'm going to go into for this, but you might imagine in a more formal results setting, you could, once you have the value function across a bunch of different states, you could kind of build things on top of it to try and assess player and line performance, stuff like that. And I'll also mention that so the state action value network compared to the value function, when you kind of compare those different things, so the value of taking action in a specific state minus the value of being in a state ultimately recovers the advantage function in reinforcement learning. So there's also some nice things that kind of fall out of that in terms of equating reinforcement learning and kind of techniques we know to help learn different values with kind of the framework that we have here. With that, that's kind of the little technical aside in learning value functions. Are there any questions in that little part?
I'll ask one again. From those pictures, were there any that were surprising?
I mean, I learned that carries only happen on the blue lines and red lines in the event data that we have. This is actually an older version of this model, so we actually went and kind of changed what events we were considering because there were things like that. I thought the state action value of dump-ins was really interesting, where you could end up with lower value, or like they have negative expected value for dumping the puck in different areas. So yeah, I found that interesting. In terms of things you don't want to be interesting, like shots having higher expected value in the offensive zone was good to see, kind of like clustered around the offensive net. So yeah.
Can you explain the dumping one from a kind of a hockey perspective? Like, can you, like,
I mean, it's kind of hard to analyze directly because it's all in expected value space. But from explaining it from like the sport, there's obviously like dumping the puck in different areas have like set up different plays, like different forechecks. So if you dump the puck in one area, it might lead to a higher probability of the other team breaking it out and then going down and getting chances on you. So whereas dumping it in from other areas might mean you have more support and you're able to like get the puck back, recover the puck a little easier. So.
Can I ask a question?
Yeah, sure.
So if you go to slide 46, you've got those colored actions. Like, you know, could a coach stitch together these individual actions into a tactic?
Yes, with the caveat being that it's all expected values because it's all in event space. So yeah, in theory, and I know there's some work that says like this player took a suboptimal action because they shot the puck or they passed the puck in an area where a shot had higher expected value. Obviously, like it depends on whatever your model is constructed on top of, but like essentially in the Tactic AI paper I mentioned from DeepMind, what they do is they try and position players to defensive players to try and minimize the probability of a shot or minimize the probability of a player receiving a corner kick. So yeah, in light of this version of this type of model, I'd say, like where you try and model the expected value of different actions, there's a lot you can do tactically if you have a model that is fine-grained enough to kind of understand more of the context of an individual play.
Thanks.
Oliver?
Yeah, you just mentioned the Tactic AI paper, which is on my reading list, but since you brought it up, the Nature paper, are they doing this too? Is it that they learn a queue function and then to recommend an action, they say, oh, which action maximizes the queue function?
No. So what they don't deal with expected values. They don't deal with state action value functions or value functions. What they do is they have their model is composed of multiple different models that try and minimize or maximize the probability of different events happening. So they try and learn an expected receiver from a corner kick, and then they try and like position defending players to minimize the probability of a shot. So they treat all shots equally, and they say, okay, we just want to minimize the probability that a shot's going to happen. So they end up using a VAE, and they take as input kind of where players are, and then they project out where players would be positioned to minimize the probability of a shot. So it's somewhat similar, but they don't deal with action values. So.
And then on the dump-in versus carry, dump-in maybe something to discuss later, but I published a paper where I looked at the dump-in versus carry. It was a while ago, but from what I remember, I also found this that the dump-in is kind of fairly low, especially compared to the carry. And I looked into it and I found there's like a discussion within hockey analysts where people argue that players don't carry enough because they sort of get nervous. You know, they're like, okay, if I'm carrying, someone might take the puck away, but if I'm dumping in, it's kind of out of my hand and we'll see what happens.
Yeah.
So I think it could actually be related to an interesting kind of risk reward trade-off, you know, a sort of risk aversion.
Yeah, I think there's also a bit of selection bias there in terms of like which players choose to dump the puck in versus players that carry it. Typically you have like third or fourth line players that always dump the puck in, and then you'll have first line who never dump the puck in. So I'm sure there's some selection bias in there that you probably need to be careful about.
Wow, we've been in sync, David. I had no idea. I looked at the Sidney Crosby disproportionately carries.
Yeah.
I mean, does not dump.
I didn't have to look at the event data to figure that one out.
Well, okay,
but Connor McDavid never dumps the puck in, but other players might.
Wow, that's amazing. You and I may be the two people who've looked the most closely at event data on the issue of dump-ins. Yeah, I find it very interesting. Okay, but it does sort of come out of the model. I guess what I'm saying is my model is kind of saying similar things to what your model is finding.
Yeah, that's great.
Okay,
David, are you enforcing symmetry constraints, or does the data express that naturally, and then the system says, "Gosh, this looks symmetric, so I'll just assume it's symmetric"?
No, they're enforced. It's symmetric, but on the y-axis. So good catch. There are models like I had initially built it without symmetry, and then I figured like a model like this, like a simple first approach at this, should kind of reinforce symmetry, and then like as you get more complex in the state space, you could obviously like remove that requirement and kind of look at different patterns. So
it certainly seems to make sense, at least as a first pass, and then little nuances might be team by team and player by player preferences for one side or the other.
Exactly. Yeah, for sure.
Okay, thank you.
Yeah, good comment. Okay, so I think I have a bit of time. I'll try and go through this quickly, but so I'm going to get into some work I did with tracking data in my time at Waterloo. Kind of all the hockey stuff I did at Waterloo wasn't actually part of my dissertation. So like my dissertation is the impact of teams and multi-agent systems, has nothing to do with sports for the most part. So I have the little Waterloo insignia up here, just because a lot of this work, it's published, it's all public work, done through collaboration with my advisor at Waterloo during my time there. And so the idea here is we kind of want to measure the available space between a passer P and receiver R using the tracking data. And so more motivation here is kind of in the initial motivation behind the project was traditional stats typically tend to bias offensive players. And so we thought we could probably use the tracking data to kind of augment traditional stat lines to provide more context to how players perform with the puck. And so this might provide insight into players' risk levels, their skill levels, and also their decision-making. And to solve this, we lean on Euclidean geometry, so there's no reinforcement learning or deep learning in this, but the outputs of these models can help inform, say, player evaluation models, or augment the state space that I mentioned in those previous models. So for example, on the left here, we have a little diagram. The passer's trying to give the puck to the receiver, and we have an opponent in red. And so a large lane might be when this opponent's far from the direct pass. Then the lane, as the opponent moves closer to the direct passing line, the lane gets smaller and smaller until there's maybe no lane. And so we construct a model to try and characterize the overall situation of the pass that satisfies 4 key characteristics that we define. So the first, imagine we have a passer P moving the puck to R. If the receiver were to move further away, you might imagine this pass would become more difficult. So if the receiver is 100 feet away versus 10 feet away, you might imagine that the pass that's 100 feet away is more difficult. And so the first requirement that we identify is that the passing lane should scale with respect to the pass length. Moving on, now assume we have opponents in the situation, as we commonly do, and assume that opponent 1 and opponent 2 are equidistant from the direct passing line from P to R. In this scenario, opponent 2 actually has more time to intercept this pass or to influence this pass. And so the second requirement we identify is that whatever passing lane we come up with should be asymmetric with respect to the pass direction. And so you might think, okay, using a triangle here, or a cone might actually do a good job, because then opponent 1 would have to be closer to the passing line to have the same influence that opponent 2 would. However, if there are more opponents that are outside of what we define as the passing corridor, or between P and R, this vertical space, opponent 3 and opponent 4 could actually influence the ability for this pass to be made. And so you might think, okay, let's just take the area around the passer and receiver into account here, and we're good to go. And so the area is, or the third requirement is that we should consider the area around the passer and receiver, along with kind of this asymmetric shape in the direction of the pass. And so what we end up coming to is this kind of collection of circles and tangent arcs, and you can take kind of the intersection of all of these to define an actual passing lane shape. And that's the shaded region here. And the nice thing about this model is that there's only one parameter that measures the size and the shape of this actual shape here. And so we define that to be gamma. And the size and shape of this gamma fits to the surrounding opponents. And then, so this is heavily inspired by alpha shapes and beta skeletons in Euclidean geometry, where they kind of fit to the internal structures of things. And so you might imagine here, like, if opponent 4, so this shape here is fit to opponent 2, but say opponent 4 skates closer to the receiver. So now they're inside of whatever shape we have defined with gamma equals 0.31. What would then happen is the passing lane is defined as this, where gamma equals 0.15. So depending on the locations of all the opponents, the gamma actually fits to the most threatening opponent. And so the fourth requirement here is that the model should always assign a real numbered value. And the motivation behind that is that we then can aggregate across all passes in all different context for players instead of having like infinite values or null values or anything. So in reality, we can calculate the size and shape of and this value of gamma. We can calculate that directly. But to just try and characterize how fitting to the surrounding opponents might look, imagine we have a passer P, receiver R, and these two opponents. When gamma is 0, it's just the direct passing line. And then what you might think is like, okay, we'll just increase gamma all the way until we contact the nearest opponent. And so this is just a visualization of what the passing lane model looks like. And so this final shape here where gamma equals 0.55 is determined by opponent 1. And this is the overall size of the passing lane, or value of the passing lane. In follow-up work, we ended up extending this to not just direct passes, but the unique thing about ice hockey is you can make indirect passes off the boards. So the way we do this is we reflect the ice across a bunch of different, or the boards in a bunch of different directions, and then we fit the passing lane as a direct pass with respect to the real opponent location and the reflected opponent location. And we take the minimum of those as the passing lane value. So here the passing lane fits to the reflected opponent. And we also took into account the expected movement of players. So a pass isn't an instantaneous event. A pass takes time. And so what we do is we project the receiver forward to a projected location, R prime, depending on the distance between P and R. And we take the expected duration of that pass, project the receiver forward. And then we also project the opponents forward in time. But the interesting thing about opponents is that they can really only influence a pass up until the puck passes them. If the puck's already past them, it doesn't matter where they go. So we end up taking the dot product from the opponent onto the direct passing line here, shown here. And then we take the amount of time that it would take for the puck to get there, and we just project the opponent forward for that amount of time, which is when they're in the passing corridor, it's a fraction of whatever the expected pass duration is. And so what we do is we have O prime and R prime, and we do this for all different opponents, and then we end up fitting the passing lane model to these expected areas. And so hopefully this slide works, but this is kind of a GIF showing a real game scenario modeling passing lanes for direct passes and indirect passes. And so what the numbers here represent over the players is the highest passing lane value for all their options. So here you can see for 91, for 47 to 91, we project out the most available pass, and it ends up being off the boards right as the moment that 47 makes this pass off the boards. And 91 receives it, and then they go in and they score. They do a nice move. So to evaluate this model, I'm just going to show a handful of results. This is over the 21-22 season, over 1,300 games. Our data set consists of 750 players, 478 forwards, 272 defensemen. And we filter our results to only players that played at least 10 games and averaged over 10 minutes of ice time per game. Some very quick two main results that we have. On the left, we show a CDF plot where we have the average PAA, which is the passing lane availability over their passes along the x-axis, and then the fraction of the population along the y-axis. And what we find is that forwards, which are the blue dash line, tend to complete, the red line, tend to complete passes with slightly smaller passing lanes. So the distribution is further left than the defenseman. And then on the right, we have the average PAA, which is the passing lane value for a player's passes. And we kind of cross-reference that with assists 82. So this is a player's assist projected to 82 games. And I think we also projected to 15 or 20 minutes of ice time per game. And we found this really interesting pattern where no players that had high values or high numbers of assists, high projected numbers of assists, also averaged high passing lane values. So really big passing lane values. the players with really high assists all kind of had smaller passing lane values. So it might indicate some notion of passing skill. So that's it for these three areas. In summary, kind of going back to how this talk began, there's no shortage of multi-agent problems in invasion games. Kind of the interaction between a passer, receiver, opponents, though you could think of that as a multi-agent problem in the kind of value function work. The interaction of multiple teams kind of formulating that zero-sum game, that's a multi-agent system. Advancements at both in both multi-agent systems and sports, and kind of the intersection of the two will really drive both fields forward. As I kind of displayed, we get a lot of real data for cooperation, financial transactions, the development of agents and players through time. With the coaching management thing, there's multiple levels of planning required for success in invasion games. And then also, like, it's kind of cool that we get rewards too if we're successful. It's not just like our agents getting rewards in the game. The rewards in sports are pretty cool, especially the middle one. And so in closing, some of the research interests I have now that I've transitioned into industry, say, or like into working in the NHL, I'm still very interested in learning state value functions, especially from more complex data sources and different contexts of different teams and players and what those mean. I'm really interested in offline policy evaluation for not just individual players, but groups of players, lines, maybe full teams. Understanding player and agent types and how they might fit together in team formation problems is super relevant to multi-agent systems and a really big area of interest for me. And then also empirical game theory. So we obviously have two adversarial teams, agents, coaches making decisions and how they choose who plays against who. There's a lot of influence from coaches in games and also just kind of like tactical decisions. And so I think there's some interesting work in empirical game theory there. This QR code is to that Blue Sky paper that was published at AMOS last year. And then you can also go to my website and find, or my Google Scholar or something, and find all the other hockey related papers, not the value function stuff, but all the work I did while I was at Waterloo on passing lanes. And a shout out finally to all my great collaborators on a lot of the work, my advisor, Tim Brecht at Waterloo. My brother, actually, Dan Radke, was big in a lot of the passing lane stuff. He does computational geometry, so he was really big in developing that. Yeah, my collaborator, Alexi Orchard at Waterloo, who helped me with the multi-agent challenges and help kind of scope out that position paper for AMOS last year. So thank you.
Great, thanks very much, David. I just want to apologize if you hear jackhammering. It's right below me in my house right now, and it's very inconvenient timing. But anyway, I'll just have to maybe quickly mute myself if it comes back. So if you have questions, please unmute yourself, just ask away, or you can put it in the chat if you'd rather that I deal with it. So I'm going to start with a question.
Yeah.
So you talked about, so obviously there's a lot of like learning, being discussed within AI. And so I'm curious, how do you set your rates of learning? How are those parameters determined?
So are you talking about like learning rates specifically, or like different hyperparameters in models?
So I'm not very familiar with the AI, like I'm thinking, if there's a learning process, like you need players or teams to learn, how fast can they learn within the context of your models?
Okay, all right. Now I'm going to ask another question. Are you talking about like the actual players and coaches learning, or are you talking about the models learning?
Well, I guess both. So I'm coming at this from complete ignorance. So maybe, you'll have to sort of give context to your answers. But like, I suppose, well, maybe could you distinguish the two? So when you talk about models and learning, like this is you're giving them more data, so they're obviously going to get better and better. Is that sort of
Yeah.
model?
Yeah, and
model
obviously there's a lot of hyperparameters too in terms of like learning state value functions or state action value functions. A lot of those are when you're learning from reward. So you have some model of a reward in an environment and you're learning from reward. There's a lot of say a learning rate plays a big part, a discount factor plays a big part in how much you want to discount future rewards. There's tons of literature in the area of reinforcement learning that talks about how to set those like discount rates and stuff. For the most part, a lot of like hyperparameter tuning and stuff just kind of depends on the context of building out models, a lot of trial and error. In terms of like, I don't know how to approach the second part of that, like how would teams and players learn? There are obviously like different ways to use these models. You could use them to evaluate players, kind of how I talked about the passing lane work. But you could also identify strengths and weaknesses. So depending on whatever setting you're in to approach players, you might be able to present strengths and weaknesses to maybe help them improve in certain parts of their game. So that's me coming from it as like a pure researcher perspective and not like someone who represents the Blackhawks. Like I don't think I'm at liberty to say anything in terms of like how the coaches and players at the Blackhawks would use this sort of thing. That's just me kind of hypothesizing how models like this would be helpful. So. Any other questions?
Yeah, I have okay, I'm probably the closest, so I have a few. Let me maybe ask just a couple of technical things. So you say you learn the value function with the neural network. So I'm guessing you don't estimate transition probabilities, right? Is it something like temporal difference learning to fit the function?
Yeah, it's a straight up value-based approach. So yeah, we don't estimate transition probabilities. We just learn it straight from the reward model, or like reward function, I guess.
And you said for the passing lane work, you use tracking data in hockey. Did you also think about using tracking data to learn a value function instead of the eventing?
Yes. At the time, so the passing lane work was kind of priority at the time I was at Waterloo, building out the passing lane stuff. So we didn't kind of get into more of like the state value function work. But yeah, you could. That like what I mentioned, where it's like it all kind of depends on whatever context of the state you want to boil into the state space. Like obviously tracking data gives you more context. And so you could essentially you could essentially use tracking data to do that. But yeah, it's not something that I did in the work that I showed here. The work here was basically just like let's take an event data set and kind of see what type of expected values we could learn from it, given some notion of a reward model.
Yeah, and I think we're usually all curious, and maybe you just cannot say anything about what you're doing for the Blackhawks, but maybe to explain a bit where I'm coming from, I talk to people come to the seminar. We've had analysts with teams, with Hockey Canada. I talk to, any chance I get, I go to conferences. And, I think I've got like a 5-minute spiel now on reinforcement learning and how you can use it. But still, they seem so far, what they're trying to do in practice seems so far from anything like that, learning a value function, for example. I'm just, is there, I guess it's like some kind of connection, or have you, this, like your secret identity now is multi-agent RL, where you go out at night and solve the problems.
Do you mean like how would I explain this approach to people who aren't familiar with it?
Well, I guess I'm generally curious what you're doing for the Blackhawks, and then in particular whether RL or
Yeah,
comes into this at all.
I don't know if I'm at liberty to say like what I'm specifically doing in-house and what I'm working on. But I think in terms of explaining, I think like a lot of the thoughts that you're having are kind of the main motivation behind this multi-agent challenges paper. I found myself, like I worked for the Blackhawks for the last year of my PhD, and I found myself at conferences talking to people within AI, within multi-agent systems, about working for the Blackhawks. And a lot of them didn't understand why, and they didn't really conceptualize the problems that would be in a sporting environment. Whereas I don't know if it's because I played sports or I kind of like was doing research while I was playing. Like I kind of like if you read that paper, it's really trying to say what I said in the beginning of this talk, where it's like there's all of these problems in sports that exist that teams have been trying to solve for decades. That it's always an important topic. And then there's all of these areas in multi-agent systems and in reinforcement learning, not just multi-agent RL, but also like single agent RL, like value decomposition is an interesting one. And there's like all of this like really interesting research in that area. And these are all the same problem, essentially. And so, yeah, I think kind of like what you're getting at is a lot of the motivation behind why we wrote that Blue Sky paper. So
Maybe I could just quickly follow up on Oliver's question. Like, yeah, I know you can't discuss details, but I have a more general question. Like, I can imagine early on in analytics, like just getting data and producing some numbers was sort of where analytics were at in the industry. And so like how sophisticated have things gotten, amongst NHL, maybe not even NHL teams, but even in other professional leagues in terms of using these very advanced or, like research grade statistics and computer science inspired modeling methods.
yeah, I mean, I think it's like the easiest example is to just look at baseball and look at you look at kind of the impact that baseball has had in kind of the development of analytics, not just like in-house, but like in how the game is played. Like they completely changed the shift. They got rid of the shift out of like they put in a rule so that you couldn't shift anymore because analytics had I guess gotten to a point so much to where teams were completely changing how they set up defensively. Teams now in baseball have dozens and dozens of people working within the front offices, like upwards of 45 people working as analysts in the front office. That's obviously like that's a different perspective of it because they've kind of obviously there's tracking data in baseball on the defensive side of like where players are positioned and stuff, but if you just think about like the really low level event data that you could get at baseball, it's obviously like carries a lot more information than event data in a sport like hockey or soccer. So there's a lot more of these statistical models you can build earlier on, and they've kind of obviously had a big impact in the sport.
But how sophisticated? Like, I mean, so like it sounds like so I guess my question is like you can make lots of decisions based on analytics, but you can make lots of decisions based on either simple analytics or more complex analytics. And I guess my question is how complex are the analytics getting? Is it like and it sort of also relates to your role as your title as a research scientist. So presumably you're not, you're actually doing research that's, maybe slower in nature to bear fruit than a frontline analyst who's like producing the numbers. Like in my, I'm more of a sports scientist. So just, like distance covered by a player to measure potentially like fatigue or, training loads and things like this. Like these are simple sports science approaches versus like analytic approaches where you're using very complex models and computing and such. Do you have a sense of that?
Yeah. So I'll kind of add, like, ultimately, whatever comes out of our work needs to be communicated effectively, right? Because it's like, we're not the ones making trades, we're not the ones signing players for millions of dollars. So it's like, whatever comes out of the sophisticated models we come up with obviously needs to be explainable and needs to be communicated in a way that's very effective. I would say, I can't speak to any teams, any other teams or any other situations, but I mean, looking at other sports again, like baseball has R&D departments that are currently like they might not be called research scientists, but they have R&D departments that develop in-house tools that influence decisions that they make. If you look at soccer, like Liverpool has / I think had the collaboration with DeepMind, where they had 20 research scientists working on problems related to tracking data, and it was a very very interesting setup they had, because a lot of people in that group were multi-agent researchers. So they had kind of that perspective in that collaboration to be like, this is a multi-agent problem, let's just do research in this collaboration. I think it comes down to resources, like which teams have the resources to be able to kind of consider doing cutting edge long-term research like that. Obviously in a collaboration like Liverpool and DeepMind, it's a little different. But not to say that like other teams in the Premier League or like around the world in soccer don't have people in-house that are doing fundamental research. There's a lot of collaborations with like academic labs that, like, soccer has a lot of papers coming out doing soccer research with tracking data, or or just event data. Like, there's a lot of interesting work coming out about soccer in Europe. So to your point, I think like teams are always fuzzy because a lot of it stays in-house. In terms of cutting edge research with data with sports, I think there's a lot of research being done. But at the end of the day, it all probably needs to be communicated in an effective way so that the people who need to make decisions based on it can actually make effective decisions. And that we have that we have the confidence to say, like, yes, our model is learning this and it's all in expected space, but whatever we do with that ultimately has this meaning at the end of the day. So
yeah, that's great. Thank you for. So I guess a question to follow up is, like, how do you communicate, your models effectively, especially when you get into, like, so, like, you can imagine some of these, your front office staff have they took a statistics course back in the day, maybe they're business, or they're from a business school or something, where there's some quantitative sophistication,
yeah.
but they aren't computer scientists, right? Like, there's a lot of jargon and a lot of uncertainty too with the model outputs and how you interpret these very abstract results. So do you have any advice for budding sports analysts on how to communicate sophisticated results or results from sophisticated models to front office staff?
I mean, yeah, ultimately, like, data literacy is obviously like a huge hurdle, I guess, like not even just for front office staff, but like in general, like understanding what model outputs are supposed to mean and how they're supposed to be interpreted. Data literacy obviously is a big thing. If a model is 80%, like if you say this is going to happen with 80% probability and it doesn't happen, like you obviously need people to understand that, like, there is a 20% chance that thing isn't going to happen. So that's big. I'd say, like, ultimately, in terms of written communication, so this is something I had to learn in grad school, where it's like no one knows the model that you're developing as good as you. And so when I was writing papers and throughout grad school, I really had to learn an effective way of how to handhold through all of the results, all of whatever whatever I'm presenting. Even in an oral presentation, like having things that pop up. You guys probably noticed that a lot of things that pop up because hand-holding through what you're trying to communicate to people is super effective. And that's just kind of something I learned through grad school, is how to actually communicate new ideas. So that's probably the best advice I can give, is like, you obviously need some notion of data literacy to try and communicate like high level ideas to people. But then at the end of the day, it's kind of up to you as a researcher to make sure that one, your model can actually be understood by whatever you're doing can be understood by a population of people. And then at the end of the day, you obviously need to not assume that they have like below a reasonable amount of prior knowledge, and just like, or above a reasonable amount of prior knowledge, and really just handhold through the whole process as much as you can. So.
Well, I definitely appreciated that approach in your talk today, for not being in your field. Are there any other questions from the audience? Okay, well, on that note, we're going to thank you very much, David, for the time and for an excellent talk and taking all our questions. So I'm just going to stop the recording, and but yeah, thanks again.
Cool. Thanks for having me.
Okay.
Yeah, great.
Yeah.